Okay, so in this video we're going to look specifically at transformers, which is a device that makes use of electromagnetic induction in order to exchange voltage and current. So let's start off with what a transformer actually looks like. So there are three key parts to a transformer. So the first key part is we've got something we call the primary coil, which is the input side. So whatever voltage and current we're starting with will be connected to this primary coil. We've got the secondary coil, or the output. So this is essentially what we connect to whatever it is we're trying to supply with a different voltage or current. So if we're using a mobile phone charger, for example, which makes use of a transformer, the primary side would be connected to the national grid. You plug it into your socket. The secondary side is the one you plug into your phone. And connecting the two, we have a iron core, and more specifically a soft iron core, and the soft is important to do that. So those are the three key parts: two coils and a soft iron core. So, as I said, a transformer makes use of electromagnetic induction. So this is why we have to supply an alternating EMF, because all of the parts are stationary. So to get a changing magnetic field to induce an EMF, we need an alternating field. So that's why we've got alternating EMF. We want an alternating magnetic field supplied by the primary coil. And the reason we need that is so we get induction, and the way we create a alternating magnetic field is to have an alternating current in the primary coil, and I looked at that in my previous video. Okay, so those are the key parts, and this is what we have to put in. So we must put in an alternating EMF. Luckily, our national grid is already alternating. The way generators work produces an alternating EMF, so that's fairly easy to do in practical terms. Okay, so why do we have the iron core in there? So the primary coil is connected to an alternating EMF and produces an alternating magnetic field. So this is where the iron core comes in. So the iron core gets magnetized by the alternating magnetic field around the primary coil. So essentially, the primary coil turns the iron core into a magnet, and it's an alternating magnet because the primary coil has an alternating current. So then what happens is the alternating magnetic field around the core cuts through the secondary coil, inducing an alternating EMF. So that's the process. The primary coil magnetizes the core. The magnetic field around the core induces the EMF in the secondary coil. So we could make a transformer without the iron core. We could just put the primary and secondary cores close to each other, but the soft iron core amplifies the magnetic field. So you get a much stronger magnetic field with the iron core. So that's why we include it. It makes the whole thing more efficient. Okay, so how do we change the secondary EMF? So the purpose of a transformer is to take one voltage and turn it into a different voltage, either stepping it up or stepping it down. So how does that actually work? Well, this is all about induction. So if you increase the number of turns on the secondary coil, the EMF induced is increased. Why? Well, because the magnetic field lines are cutting through more conductors. And if we've got those conductors all connected in series, like a coil essentially is, that's going to produce a bigger EMF. So this is why all the stuff we've done previously on induction was needed before we started looking at transformers. So that's as a general picture, what's going on. So before we look at the next part and look in a bit more detail at the equations to do with transformers, I want to very quickly explain the difference between what we call voltage and what we call potential difference. Because up until this point, these two words have been used interchangeably because it really hasn't mattered, but now it actually becomes important, the difference between them. So voltage means the energy each coulomb of charge has at a certain point. So we can't really measure this, but at a certain point in the circuit, the charges will have a certain amount of energy, and that's what we call the voltage. Potential difference tells you how much the energy changes as the coulombs go through a component. So if a coulomb loses 1 joule as it goes through a component, we say that's a potential difference of 1 volt. So with transformers, the V in the equations that we're going to have stands for voltage, or the amount of energy that each charge has at a given point, whereas previously the V has stood for potential difference. So to make it really crystal clear in this video, I'm going to use V for voltage, and I'm going to use delta V for potential difference, so that I can show them in equations and we don't get them mixed up. Because essentially what a transformer does is it exchanges current for energy. So essentially what you can do with a transformer is increase the amount of energy a charge is carrying, but the consequence of that is you get fewer charges per second. That's the general picture. So how can the output voltage be determined? Okay, so essentially output voltage is decided by the turns ratio. So if you look on these transformer diagrams you've got here, primary side has 5 turns, secondary side has 20 turns, so it gives us a turns ratio of 4, because it's essentially 1 to 4. And so that ratio determines what the output voltage is going to be. And the ratios are exactly the same. So if this NS is the number of turns on the secondary side, this NP is the number of turns on the primary side, so you can see that the turns ratio is equal to the voltage ratio. So what does that mean? If you have double the turns on the secondary side compared to the primary side, you get double the voltage on the secondary side, the primary side. So let's see some examples of that. So we've got this one on the left-hand side. So what we can do is calculate the turns ratio, which you can see is 20 divided by 5, which is 4, which means that the voltage ratio is also 4. So if we wanted to know the voltage on the secondary side, it's 4 times the voltage on the primary side. Voltage on the primary side is 100, so you can see it comes out as 400 volts, which you can see up here on the diagram. So that's all worked out correctly. We can do the same thing with a step-down transformer. So you can notice on a step-up transformer, we increased the voltage at the expense of current. Step down, we should essentially get the opposite, but let's try it out. So again, we can calculate the turns ratio. This time it's 10 divided by 50, which is 0.2. So that means that the secondary voltage is going to be 0.2 times the primary voltage, which is 1000, which you can see comes out as 200 volts. So we can see that it matches up again with the diagram, but again, so this time we've stepped down the voltage, and so you can see we've increased the current. That's always the trade-off. Whatever happens to one, the opposite happens to the other. That's the idea. Okay, so those are some examples of using the turns ratio. Okay, so we've seen how we can determine the output voltage. How can we determine the output current as well? Well, we're going to use conservation of energy. Well, power in equals power out. So that's our starting point. Power in is equal to power out. So what that means is that the current times the voltage on the primary side is equal to the current times the voltage on the secondary side. And this is voltage, not potential difference. So I'm using the symbol V, so I'm using that for voltage. So if we want to work out the current on the secondary side, all we need to know is what the voltage ratio is. And we can then times that by the current on the primary side. And that would give us the current on the secondary side. So this is just using the conservation of energy. So we're assuming that no energy is lost, because we've got electrical energy going in is equal to the electrical energy going out. So we're assuming a 100% efficient transformer here. Okay. So then if we know or can measure these 3 things, we can then determine the output current, essentially. And the reason we need to use this method and not some circuitry law is a transformer is not an electrical circuit. Remember, it's basically a magnetic circuit, because we've got electromagnetic induction. So that's why we needed a new method for doing these calculations. Okay, so that's how we get current. So I said we're going to assume the transformer is 100% efficient. Okay. So that's what we used in determining the output current. but a actual transformer is not 100% efficient. It's very close to it, actually. They're well in excess of 99. But why might it not be 100% efficient? Well, there's two main reasons we can look at. So the first is about essentially Lenz's law and Faraday's law. So iron is a conductor. So the alternating magnetic field in the primary coil can induce a current in it. Okay, so we've got an alternating field cutting through a conductor, we're going to get a current. And remember, when we get a current in a conductor, we can produce thermal energy. What we'll get is electrical energy converted to thermal energy. So that's one source of losses here. The second one is the magnetization or demagnetization process occurring in the iron core requires energy. If you want to turn something into a magnet, you have to supply energy. We usually do that. So what we've seen previously when we magnetize nails is we were stroking it with the magnet. So we are doing work. So we are supplying the energy in that case. But if that requires energy, that's going to reduce the efficiency of the transformer. But as I said, transformers are still over 99% efficient. So the approximation we made in the previous slide is perfectly valid. Okay, great. So we've looked at how we model a transformer, and we've sort of explained what a step-up and step transformer does. But why do we actually want to use transformers? What's the advantage of that? So the main advantage is in power transmission. So in a transmission line, if the current is reduced, this is going to significantly reduce the electrical energy transferred to thermal energy in the conductor. So how do we actually know that? What equations do we know that are going to help us with this? Previously, you will have met that the power lost as thermal energy in a conductor is current times by potential difference. So we used the P equals IV previously because we wanted the power input or the power output. This is the power lost in a conductor. And we also know that the potential difference is equal to the current times by the resistance. So if we put both of these together, we get that the power is equal to I squared R. So you can see that if we can reduce the current in a transmission line, we can reduce the power lost as thermal energy in that transmission line. So let's just annotate this quickly there. So this is power lost in conductor. Okay, and so that's what we've calculated over here, the power lost in the conductor. Okay, so that's our explanation of why we use transformers. Because we want to transmit energy over very long distances, because our power plants are miles away from our cities, because we don't like looking or smelling them, we have to use transmission lines, and this is why we want transformers, to give us very high voltages in our transmission lines, which means we've got very low current in our transmission lines. They're usually about 400 kilovolts, typically cross-country power cables. Okay, so you might previously have met another power equation, P equals V squared over R. And this equation causes people a lot of bother with transformers because they're like, well, doesn't high voltage mean high transmission losses? So the first key thing to address is, in this equation you've met before, the V did not stand for voltage, it stands for potential difference, or the energy change in each coulomb as it passes through components. That's our problem. So the first question you might want to ask is, where does this equation actually come from? You might not have seen this one before. So we're going to start with the same two equations we had previously, that the power lost in something is equal to the current times the potential difference across it, and the potential difference is current times by resistance. So what we're going to do is we're going to rearrange that to give us an expression for current, and then we can substitute that into this expression here and get this equation here. So this is where the equation, and this is why it has potential difference in it, not voltage, because we're calculating the power lost across a component here. So how can we now use this to fit with what we've just said? Well, we know that the potential difference is current times resistance. So if current is small and in a conductor resistance is small, that's going to mean the potential difference across the transmission line, or the change in voltage across the transmission line, is very small. So that's going to give us a small power loss in that transmission line. So this equation predicts exactly the same thing the previous equation did. We have to be mindful that this in the expression is delta V, or potential difference. Okay, so we've got an example now where we're looking at how electricity integrates with a transformer. So we've got a transmission line connected with a transformer with a secondary voltage of 100 kV, or 10 to the 5 volts, current of 0.01, resistance of 0.1, and it wants the voltage at the other end of the wire. So what I'm going to do first is I'm going to calculate the potential difference, or the change in voltage across the wire. So that's 0.010 times 0.1, which is 10 to the minus 3 volts. And remember, in a wire, we are losing energy. So I'm actually going to write this as minus 10 to the minus 3, because the voltage is decreasing across the wire. We know the potential difference, or the change in voltage, is going to be the final voltage minus the initial. So if we want the final voltage, we're going to need the initial one plus the potential difference. So this is why it's important that we had the minus sign in front of here, because remember, the change is decreasing. So we started at 10 to the power of 5 volts. We lost 10 to the minus 3 volts. So that is essentially just going to be 10 to the 5 volts at the other end, because the loss is completely insignificant compared to the actual voltage itself. So at the other end of the wire, we're going to get pretty much exactly the same voltage. We've lost very little voltage across it, which is the idea with a transmission line. We want to have very, very small losses, and we have very small losses because the current is so small. So that kind of makes sense.